Dear students, so in this class, now let us discuss about a monotone function. So what is a monotone? Monotone means it is either increasing or decreasing. So consider letter A is a part of R. Define a function f from A to 1. Then the function is letter for x1 and x2 present in A. So when x1 less than or equals x2, then if f of x1 less than or equals f of x2, then f is said to be monotonically increasing, or f is said to be an increasing function. A is a part of R, f is from A to 1. Then for any two x1, x2 fallen A with x1 less than or equals x2, such that f of x1 less than or equals f of x2, then f is said to be an increasing function. F is said to be an increasing function. F is increasing. Now, if this x1 strictly less than x2, then f of x1 strictly less than f of x2, then f is a strictly increasing function. Here f is an increasing function, here f is a strictly increasing function. Also, when x1 less than or equals x2, then if it implies f of x1 greater than or equals f of x2, here f is a decreasing function. F is decreasing. If x1 strictly less than x2, then if that implies f of x1 strictly greater than f of x2, then f is a strictly decreasing function. So these are increasing and decreasing functions. If x1 less than or equals x2 and f of x1 less than or equals f of x2, f is increasing. If x1 less than or equals x2 and f of x1 greater than or equals f of x2, then f is a decreasing function. If the strict inequality holds, then the function is strictly increasing as well as strictly decreasing. So, a function f is monotonically increasing or monotonic function. What is monotone? If it is either increasing or decreasing. If a function, suppose f is a function which is either increasing or decreasing, then f is said to be a monotone function. Monotone means it is either increasing or decreasing. If f is strictly increasing or it is strictly decreasing, then f is said to be a strictly monotone function. So this is the meaning of monotone. F is monotonic means either it is monotonically increasing or it is monotonically decreasing. Then, if f is increasing, what about a minus f? If f is increasing, what about a minus f? F is increasing means the condition holds. That is, when x1 less than or equals x2, f of x1 less than or equals f of x2. So f is increasing. That means if x1 less than or equals x2, then f of x1 less than or equals f of x2. What about minus f? So this means minus f of, if you multiply throughout by negative minus 1, what I get? Minus f of x1 greater than or equals minus f of x2. The inequality reverses. So come to the conditions. That is, when x1 less than or equals x2, then minus f of x1 greater than or equals minus f of x2. That means minus f is a decreasing function. So when f is increasing implies minus f is a decreasing function. Okay. Similarly, when f is a decreasing function, if f is a decreasing function, what happens? If f is a decreasing function means for x1 less than or equals x2, f of x1 greater than or equals f of x2. So this is the definition of decreasing. What about a minus f? If you multiply throughout by negative, what you get? So means minus f of x2, minus f of x1 less than or equals minus f of x2. That means for x1 less than or equals x2, then minus f of x1 less than or equals minus f of x2, that means minus f is an increasing function. So our conclusion is, when f is decreasing, then that should imply minus f is an increasing function. So these are important research. If f is an increasing function, minus f is a decreasing function. Why? Because of these arguments. If f is a decreasing function, then minus f is an increasing function, and vice versa. Okay. Right. Now, a monotone functions are not necessarily continuous functions. Monotone functions are not necessarily continuous. It may be continuous, but it need not be continuous. Not necessarily a continuous function. If you define a function in step function form, then you can prove it easily. Now let us consider a research. Come to a theorem. The theorem states that let I is an interval. I be an interval means it's a part of form. F is an increasing function on I. F is increasing on I. Then let C fall in I. Let C fall in I, which is not an endpoint of I. C is not an endpoint of I. I is an interval. This is I. Suppose this is I. So C presents in I. C is not an endpoint. C lies in, or C is any point that between the endpoints. C is not an endpoint of I. Then limit. Then the theorem states that limit x tends to C plus, that is the right side limit. X tends to C plus f equals infimum set of all x fall in I such that, or infimum set of all f of x. Infimum of f of x for all x fall in I with x greater than C. X greater than C. And the left hand limit x tends to C minus of f equals the supremum f of x for all x fall in I with x less than C. So this is the theorem. So come to the hypothesis. I, what is I? I is an interval, and f is defined on I in such a way that f is an increasing function. That is, for any x1, x2 fall in I, x1 less than or equals x2, then f of x1 less than or equals f of x2. C is not an endpoint of this I, then limit x tends to C plus f and C minus f are defined in terms of infimum and supremum of such a function, not the function f. How to prove this one? So its proof is, the theorem is important. Come to the proof. We define a function, we define a set. Let A equals set of all f of x, where x fall in I with x less than C. Let A equals set of all f of x for x fall in I with x less than C. Now, x presents in C. Sorry, x less than C, not x presents in C. X less than C. X less than C. X less than C means f of x less than f of C. Why? Because f is increasing. Strictly increasing means it's also strictly increasing. It's a monotonic function. X less than C means f of x less than C or f of x less than or equals f of C. Why? Because f is an increasing function. What about A? Is A empty? No. A is always non-empty. Why? A is always non-empty because C is not an endpoint of C. C is not an endpoint of I. Since C is not an endpoint of I and A is defined as in this way, so clearly A is non-empty. A is a non-empty set. Okay. Now, f of x less than or equals f of C, and A is the collection of all such f of x with x less than C, then this, what about this A? So A is bounded above by f of C. Okay, f of x less than or equals f of c, and a is defined as set of all f of x with x following I with x less than c. So since f of x less than or equals f of c, we know that f of c or a is bounded above by f of c. F of c is an upper bound. A is bounded above. A is bounded above by f of c. Okay. A is bounded above f of c. That means A is bounded above means supremum A of x is. Supremum A has a supremum. So let the supremum A equals L. That's our assumption. That's. Let the supremum of A equals L. So now let epsilon is positive. A is the supremum of L, least upper bound. So clearly L minus epsilon is not an upper bound of A. L minus epsilon is not an upper bound of E. Clear? Why? Because L is supreme of E and epsilon is positive. No number less than this L is the supreme of E, as an upper bound of A. Therefore L minus epsilon is not an upper bound of E. Clear? That means since L minus epsilon is not an upper bound of A, there exists some y following I with a y less than c, y following I with a y less than c, such that L minus epsilon less than f of y less than L plus epsilon. Clear? Okay. Since L minus epsilon is not an upper bound of E, then there exists an y following I with a y less than c, the same condition that is given in hypothesis, such that this f of y lies in between this L minus epsilon and L plus epsilon, or simply L minus epsilon and L. Not made of L plus epsilon, only L minus epsilon less than f of y, strictly less than L. Put on delta equals c minus y less than c. So put delta equals c minus y. So c minus y is, since y less than c minus y is always positive. So delta is positive. Okay. Y less than c minus y is positive. Choose set the following I. Let us set the following I. You can choose another point, set them. Let us set them. Here it is set them. Let us set the following I. Such that set y less than set less than c. Y less than set less than c. You can choose what is y. Y is in I. With the y less than c. Okay, suppose c is here. C is not an endpoint of I. So suppose c is here. Let y is here. Then you can choose y following I with the y less than c. Okay, with the L minus epsilon. What is L? L is the supreme of A. Then with L minus epsilon less than f of y less than. Here you can choose set following I, with set lies in between this y and c. But what is f? F is increasing on I, and y less than set less than c. That means f of y less than or equals f of z less than f of c. F of y less than inequality. That is not meant. F of y is strictly less than f of z strictly less than f of c. Why? Because f is an increasing function. So that means what is L minus epsilon? But L minus epsilon combines these two results. L minus epsilon less than f of y less than L. Also f of y less than f of z less than f of c. So if you combine, what you get? It is L minus epsilon, this L minus epsilon less than f of y, but f of y less than f of z, f of y less than or equals f of z, whatever may be, strictly less than, which is strictly less than, what is f of z? Strictly less than f of c. Okay, L minus epsilon less than f of y less than f of z, and so which is strictly less than L, or f of y strictly less than L minus epsilon strictly less than f of, so L minus epsilon less than f of y less than f of z less than L. Okay, so that means modulus of f of z minus L strictly less than epsilon. Clear? So that means f of z lies in where f of z represents in yes, L minus epsilon and L plus epsilon. F of z represents in open interval L minus epsilon and L plus epsilon. So if z fall in I, now again you can choose z. Z fall in I, how to choose this z? Z fall in I such that with a y less than z less than c. Z fall in I such that y less than z less than c, then f of z, then we obtained f of z fall in L minus epsilon and the open interval L minus epsilon, L plus epsilon. Consider y less than z. Y less than z. Y less than z, that means minus y greater than minus z. Okay. So that means c minus y greater than c minus z. Clear? What is c minus y? That is delta. That means delta greater than c minus z. Delta greater than c minus z. So delta greater than c minus z, or choose c minus z less than delta. Delta greater than c minus z means c minus z less than delta. For z fall in I, c minus z less than delta for z fall in I with c minus delta, c minus epsilon or c minus z, c minus delta. Here it is. That means for z fall in I, c minus z less than delta means c minus delta less than z. Okay, but this z less than c. So c minus delta less than z less than c. Then here also f of z fall in L minus epsilon and L, or L minus epsilon and L plus epsilon. Agree? Then that means if z less than, or if z minus c minus delta less than z less than c means if z fall in open interval c minus delta c, then f of z fall in open interval L minus epsilon L plus epsilon. So that means limit x tends to c plus of f equals infimum, so equals L. What is L? L means supreme of A. That is, what is L? L means supreme of A. Okay. So that is the first part. Limit x tends to c plus of f equals infimum f of x for all x fall in I with x greater than c. Clear? That is, if c minus delta and if z fall in open interval c minus delta c, then f of z fall in open interval L minus epsilon and L plus epsilon. That means if z fall in c minus delta c means x tends to c plus of f equals supremum of L. What is L? L is supreme of A. That is, L is the supreme of A. So it is limit x tends to, if z fall in c minus delta c, then f of z fall in c minus, L minus epsilon and L plus epsilon. That means z fall in c minus delta c means limit x tends to c minus of f equals supremum of A, that means L, or equals L, that means what is L here? L is supremum of A. Therefore, limit x tends to c minus f equals supremum of f of x for all x fall in I with x less than c. Similarly, you can show that it is limit x tends to c plus of f equals infimum f of x for all x fall in I with x greater than c. Okay, thank you.